Bismillahirrahmanirrahim. Electrical network analysis, and today our topic is initial value conditions for RC Transient. Okay. In all the examples in the previous section, the capacitor was uncharged before the switch was thrown. But now we examine the effect of a charge and therefore a voltage on the plate at the instant the switching action takes place. The voltage across the capacitor at this instant is called the initial value, as shown for the general waveform. So these are the initial voltages that has already been stored before the switch is thrown, and when the switch is thrown at t is equal to 0 time, we have the initial values already V1. Okay, and from there the voltage rising up, not from the 0 but from the Vi. Okay, so it means there is some initial value before the switch is thrown to 0. Okay, so now what will be the effect on the final value we see if we have the voltage Vi? Once the switch is thrown, the transient phase commences until a leveling off occur after 5 constant. This region of relatively fixed value that follows the transient response is called the steady state response, and the resulting value is called the steady state or the final value. The steady state value is found by substituting the open circuit equivalent for the capacitor and finding voltage across the capacitor. Okay, so here we have Vc is equal to E 1 minus e raised to power minus t by tau, shows the uh, uh, which is the formula for the charging phase. Okay, uh, now we have E is equal to Vf minus Vi. Okay, so 1 minus e raised to power minus t by tau. Okay, now adding the starting value of Vi, the equation results, we will get this Vi plus Vf minus Vi into this, because now we have the initial value of Vi. So solving that bracket, we will get Vf minus Vf e raised to power minus t beta plus Vi e raised to power minus t beta. Taking e raised to power minus t beta as common, we will get Vc is equal to Vf. Okay, now if we have no initial value, means Vi is equal to 0. So whether this equation will satisfy this expression for Vi is equal to 0. So let's put Vi is equal to 0 over here. So we will get this, and Vf is equal to E. Now we have the example. The capacitor in the figure given has an initial value of 4 volt. Find the mathematical expression for the voltage across the capacitor once the switch is closed. And in the B part, find the mathematical expression for the current during the transient period, and we have to sketch the initial from the initial value to the final value for the part A and B. Okay, so we have two resistors in series. We have the capacitor, but now in this case, this is different from the previous one, because now we have some voltage already stored in the capacitor before the switch is thrown to uh, close. Okay, so we have some initial value of 4 volts. So what would happen? First of all, we have to find the time constant. We have two resistors in series, so R1 plus R2 into C. Okay, now so this is 111.22. For the 5 tau, we have the value 5 multiplied by 11 point this, we will get 56.1 millisecond. Okay, now using the initial value formula, so Vc is equal to Vf plus Vi minus Vf e raised to power minus t by tau. Putting the values, the final value is 24. The initial value is 4. So we will get this. Now in the B part, we have to find the current. So now instead of E, we have E minus Vc. Okay. because we have already some voltage. So now the current will start from 24 minus 4. Okay, so E minus VC 24 minus 4, and we have two resistors in series, so adding these two resistors we will get 5.88. Okay, this is the mathematical expression. And here is the sketch. Okay, we have already 4 volts in the initial, and we will start from 4 instead of 0, and similar as exponentially rising, and it will reach to 24 volt in the 5 ta period. Okay, we have that 5 ta period is 56.1 millisecond, and similarly the current will start from 5.88. Okay, and it will goes down in the same time period of 5 ta, okay, to 0. In the C part, okay, this is the actually the sketch was the C part. Okay, if we if you want to find the value for t is equal to 0, so put the t is equal to 0 over here. So we will get 24 e raised to the power 0 in this formula. Okay, so we will get vf plus vi minus vf, which is equal to this 4 volts. Okay, and when, so at t is equal to 0 we have v is equal to 4 volt. Okay, and for t is equal to 5 ta, putting the value of 5 ta in this equation. Okay, for t is equal to 0 we have to use this equation, and for t is equal to 5 ta, this we will use the same equation as well. Okay, so we will get how much? 24 volts. Okay, okay, now for the discharge. Okay, we will have the same value vi is the initial value, which is equal to e now, and this is exponentially decaying curve for the VC, and it will decay to 0 at 5 ta, and in this case VF will be equal to 0. So using this expression, VC is equal to VF plus VI minus VF e raised to power minus t beta, we have Vf is equal to 0, because after 5 ta the capacitor will be fully discharged. So putting the value of Vf is equal to 0 over here. Okay, here and here we will get Vi e raised to power minus t beta. So the formula for the Vc in the discharge phase having some initial value. So we will have this formula Vc is equal to Vi e raised to power minus t beta, and Vi is this initial value. Okay, so that was all about the initial value condition. Okay, and this formula satisfied this equation once we put vi is equal to 0. For example, we have no value for the initial value, no initial value for the capacitor, so put vi is equal to 0 over here. Solving this equation we will get vf minus vf e raised to the power minus t beta. So taking vf common, we will get the same equation, 1 minus e raised to the power minus t by tau. Okay, the same equation as we have studied in the charging phase. The only difference is now we have the initial value for the capacitor, means some of the voltage has been already stored in the capacitor before throwing the switch to position number 1 for the charging phase. Okay, so that was all about the initial value condition for the RC charging and RC discharging. Okay, thank you.